Is that on? Can you hear now?
Yes.
Yeah. Microphones is all too complicated. In fact, he was born in Coventry some time ago, defected to Lawrence Sheriff School in Rugby, left there at the age of 16 to work for British Telecom, then went to Aston University. Subsequently, he worked at Oxford, Newcastle and Warwick before becoming Professor of Cybernetics at the University of Reading. I'm very grateful to Kevin for one thing in particular. He helped Colin Reeves and myself start a very successful sequence of conferences on neural networks and genetic algorithms some years ago. Well, as well as being an outstanding engineer and scientist, Kevin is undoubtedly a great communicator of his subject, so I think we're all looking forward to his lecture. So, Kevin?
Typical mathematician, umpteenth, isn't it? There we go. Happy Christmas, everybody. Oh, come on, sorry, come on, please. Please, happy Christmas. That's better. Thanks ever so much for inviting me along. As you said, long associations with Coventry. I thought some of you might be interested. This photo was taken in 18, what was it? So this photo was taken in Coventry. So he hasn't changed a bit, has he? And then, because we have one or two people here that have come all the way from Lawrence Sheriff at one point or another, this photo was taken in our back garden in Brighton-on-Dunsmore in, something like that, 65, I guess, there we go. So that's an introduction to myself and local history. What I'm going to be talking about, though, the title, Neural Interfaces, I'm going to be fairly liberal with it. So I'm going to talk about the things I want to talk about and ignore the things I don't want to talk about, and try and tick some of the boxes to give you a bit of an idea as to the possibilities. We're going to be skirting in and out of therapy, which is probably what you're more familiar with, using neural interfaces to help people that have some sort of neurological problem or to study the problem in some way. But also we'll be looking at concepts of enhancement, which now is becoming very much, I'd say, a topic for discussion and ethical debate. Certainly I'm presently on a committee, a Nuffield committee, that is looking at concepts with bionics and implants and the possibility of enhancement with implants, and how do we deal with that in terms of a society. Can everyone just go and have a super brain, or should there be some sort of rules or regulations? So we'll touch on those sort of things as well. If anybody does want to upgrade their intelligence, I know there's one or two got some problems with memory they wouldn't mind overcoming at the moment, just put your name down at the end, and we've got a nice table here. We'll do some experiments. We are at the end. The plan is I brought along a little experiment in sensory enhancement, and so somebody can experience an extension of their sensory range, but I will need a volunteer and some other volunteers to help towards the end. So when we come to do, and it will be a bit of an experiment, as you'll see. It may work, it may not work, depends a little bit on the person. Obviously, if they're a Coventry graduate, it's bound to work, but they may have been a student at Oxford or somewhere, and so we need a bit of sort of intellectual input to this. Right, let's start with, sorry, no more jokes like that. We're going to start now with perhaps one of the most obvious things. If you're doing some sort of neural interface in a laboratory, probably it's an EEG, electroencephalograph experiment, doing some sort of analysis. This is used in hospitals, particularly if people have different types of neurological problems. They can, epilepsy is one example, where they'll spend some time, maybe a week or two in hospital, where they have lots of electrodes on their head, and the doctors are trying to see which regions of the brain are active, what type of epilepsy is it, when does it occur, what are the stimuli that cause the seizures, those sort of things it is used for. But here's a couple of nice pictures to give you other examples. The left-hand one is, well, research, if you call it that. A lot of electrodes, partly because it makes a good magazine cover, and therefore the MIT and that are very good at those sort of things. but also is trying to pick up which regions of the brain are active when the person's listening to different types of music. So does Mozart get this part of the brain going? Does Kylie Minogue get that part? That sort of thing. The right-hand side picture is more the one you're likely to encounter in a lab, where you have maybe 20, 29 electrodes, that sort of number, and the person is trying to learn how to think in a certain way in order to drive a little buggy around. There are small versions of this you'd probably be able to get in Toys R Us and places for your kids at Christmas nowadays. It's trying to do, you have to get your brain working in a certain way. So it's a bit of a fun thing, but also it's used for research. One problem with this, if you like, is that the electrodes are picking up on signals millions of neurons are creating. So it's very much an average type of signal, and repeating that signal is very, very difficult because of the brain works, how the brain works. So the person maybe will think to drive a buggy around, and 8 times out of 10 the buggy will turn in the direction they want, and twice out of 10 it'll go in the wrong direction or won't go in any direction. So it's fine if you're driving a little buggy around in a lab, but not if you're driving a Jaguar on the motorway. It doesn't tend to, it might well be all right if you're driving in the centre of Coventry some nights and things like that, but it's not a fail-safe procedure is the point, even with the best of algorithms. There's a lot of research in that area, and it's a neat area. A lot of PhDs are now appearing. One of the most common commercial applications of neural implants, and there may be some of you in the audience that have benefited from this, Cochlear implants, now hundreds of thousands. They're around the world, very, very successful. The first research on actually stimulating the ear with certain electrical pulses, people like Volta, who have the Volt named after him and so on, were actually putting wires into their ears and making bubbling sounds. And this sort of scientists used to be very experimental in years gone by, and they did things like that. And in the 1950s and so on, the very first attempts at commercial cochlear implants appeared. Now they're relatively commonplace. I've got a nice little video if people are thinking of maybe having one in the future or want to know what's actually involved. I think this covers the best part. So this is a woman who's actually received one and her experience.
Until I was a teenager, I could hear quite well with the help of hearing aids or radio aids. And then from my mid-20s onwards, it was just a downward spiral until it became profound deafness. When I was losing my hearing, I felt very embarrassed and ashamed. But the biggest thing of all was I was frightened. The fear was enormous of this silent mode. I didn't think I'd be able to hear as well as I had done, because I didn't think there was any technology out there. At that moment in time, I believed it was just hearing aids. And then my consultant mentioned the cochlear implant. When you have the operation, you have to have an internal bit which goes inside here, and you can just see the faint outline of the scar. And this is the bit that the magnet for this connects onto that, like that. This long bit here, that has the 20 electrodes in it, and that goes into the cochlea of the ear. This is the processor, and there's a microphone in here, and that's what the sound goes into. This is the transmitter. Inside the processor, the sound is broken up into 20 different frequencies. A sound travels down here into the transmitter. The transmitter is connected to the receiver. The receiver then sends the 20 different signals down into the cochlea, where the 20 different electrodes then transmit the sound to the auditory receptor by the brain, and put them back together again to create the full sound. The sound initially is very electronic, and all you can hear is noise, and it doesn't make any sense. And it's a slow process while the brain starts to make sense of the sounds that it's hearing, and it channels them into different areas. For instance, I couldn't hear, I had never heard birds singing, so the first time I heard them, I couldn't understand what the sound was. Then once I identified what the noise was, it was easier to recognise it the second time. It's like that with all sounds. In many ways, like a child hearing for the first time. I just couldn't imagine not having it. Without it, it would just be soul destroying. You know, it's a great thing.
I think there's some interesting things, not only how well does it work, but it gives you an idea how it links up. When the first cochlear implants were developed, there were some people, scientists, said, oh, you're going to need tens of thousands of electrodes to make the connection together. The first actually had 6 or 7 and worked quite reasonably well. Now the most is about 28, 29 electrodes. Is fine. That's what you need. You don't need tens of thousands of electrodes. So what you're looking at here to communicate in terms of audio with the brain is a port, an input port. You don't need to link up with lots and lots and lots of brain cells. You don't need to plug into 100 billion brain cells. You just need to plug into a few of them, and the brain will adapt. And as we heard there from Nicola, her brain had to adapt to noises, particularly noises she had never heard before. Tinny, electronic, she described them, and her brain had to tune in and make sense of the noises by linking them to some association in the outside world. Now that then gives us opportunities, because for all of us, our brains operate in a certain way, we have certain sensory input, a very, very limited sensory input in terms of what's going on around us, but it doesn't have to stay like that, because our brains are quite adaptive, our brains are quite plastic. So if we can push a few different signals in, the opportunities are there for extending the sensory input of our brain by the same sort of approach. Now, that was cochlear implants. Visual input, which I'm sure quite a few of you are probably interested in, the eyesight going, nowhere near as well developed. Now, interestingly, some of the first experiments with, if you like, visual neuroprosthetics, a guy some of you may have heard of called Isaac Newton, used to experiment by putting small wires, can you imagine this, putting small wires into his eyeballs and trying to send in signals to generate different colours and all sorts of things. For some reason he didn't. I mean, you have to sort of read it almost in an anecdotal fashion. He didn't record all what he was doing in the same sort of documented scientific way. I mean, he was more of a theoretical scientist, apart from this experimental work he did on his eyes, which we can only deduce certain results from odd bits that he wrote here and there. But the research nowadays stems back, I think, to something like the 1950s. Now, this is a picture, quite an amazing picture, something called the Ratio Club, R-A-T-I-O, and it was like they called it a dining club. I suspect they were having a few drinks, to be perfectly honest, in London. And this guy, Giles Brindley, was one of the founding fathers for visual neuroprosthetics. In fact, for quite a few different prosthetics. So he was one of the first people in Cambridge in the 1950s carrying out research in visual neuroprosthetics. Now, the interesting thing, I like this picture because as well as him being there, this guy, some of you might recognise, this is Alan Turing, of course, and it is next year, 2012, is the 100th anniversary of his birthday. So they're starting already to get programs going. 23rd of January, there's going to be a crack at the Turing test down near London, where the Enigma code was cracked and all that sort of thing. So following in Turing's footsteps, other interesting things here. Ross Ashby was one of the founding fathers, actually a psychiatrist of cybernetics. And the one other thing of note to me anyway, this is John Westcott, who was my PhD supervisor. So it's quite a nice link. So those, you know, you have those links to links to links. So I have a link through him to Alan Turing and so on. So now you have a link. Anyway, there we go. But the visual neuroprosthetics, I've just tried to highlight perhaps some of the problems here. One of the big problems is supplying the power. It needs some sort of power supply. It's not, whereas the Cochlear, it doesn't need too much power, can work partly passively, partly with a small amount of power. You can provide the power on the outside, if you like. Not really possible. You need more power for visual neuroprosthetics and so on. And I mean, as you see here, an attempt to put the power pack actually in the eye. This is an electrode array trying to form an artificial retina. Surgery is much more of a problem. William de Bell has done research going direct, rather than into the optic nerve, directly into the brainstem. Many, many years. Much more dangerous surgery, but it's still only providing rough outlines. A lot of bright lights for the person, and they might actually be able to distinguish different letters, but it's a very sort of noddy fashion. It's not anywhere near as functional as the cochlear implants we've just been looking at there. So it's an area obviously ripe for research, but at the moment, perhaps because of the complexities, perhaps because of some of the dangers involved, it's still way, way behind the situation with cochlear implants. So big area for research. I'm now going to come on, I've called it neural, but as you see, it's sort of pseudo-neural. These are the sort of experiments you could do at home, if you like. In fact, they're experiments that some of my students are doing as part of their undergraduate project. So for some reason, I get a number of students that want to experiment with implants. Well, we get ethical approval at the University of Reading for these things to happen. I said you can try this at home. So this is Jawesh's left hand. Jawesh was the first one of the students. I've got 3 students that have magnets implanted in their fingers. And this is the guy carrying out the procedure here, the scalpel, and putting the magnets in place. You will see, though, that the guy doing it has nice tattoos on his arm, and he is, in fact, a tattoo artist. That's what his job, who goes by the name of Dr. Evil. This is true, you couldn't write this. Now this presents us with all sorts of problems, because on the ethical application form of the university, it says who carries out the medical procedure. And as soon as we put Dr. Evil, I mean, you know what committee people are like in universities, so these forms come bouncing back and we have to give all his credentials and so on. So he performs it, implants small magnets. You can see here the X-ray, 2 fingers for Jawesh, showing the small permanent magnets in place. This is actually something that's come out of the arts world. Body modification people have been implanting magnets for quite a few years, and hence a lot of the problems with the materials and moving around and things, that the arts people have had all the problems with it, and we can now pick up on that. And we're studying it scientifically, as you'll see. We're looking at it very much from a scientific point of view, but it's interesting, we don't really have scientific papers to fall back on. The papers are more arts type of papers, which is quite fun in a way. This is Jawesh showing how the thing works. So a little bit of engineering involved here. Ultrasonic sonar sensors on the baseball cap. Those are connected to a little coil of wire around his finger, in which the magnet's in his finger. So quite simply, the output from the sonar sensors is affecting the current in the coil of wire, and dependent on the distance to an object, so the magnet will vibrate or not, or vibrate more. So essentially, the closer an object comes to the sensors, to Jawesh, the more the magnet vibrates. And the further away the object, so the magnet vibrates less. So with this, Jawesh can feel how far away objects are. So it's sensory substitution. So it's the sort of thing somebody who is blind could use this to detect objects. Literally, if they had a sensor on their finger, they could point it out, detect how far objects are away, instead of using a white stick. But clearly, generally, it's a sort of an extra, different sensory input, or changing the sensory input. Now, I have a student, Ian, who has the same magnets, and what he has done, two different things. Firstly, he is using infrared as an input, rather than sonar. Now, infrared is a heat signal. So what he can do is point and detect how hot an object is remotely. So literally, he'd be able to come in here and say, you are hotter than you, are hotter and not so hot. I mean, hot in a heat sense, not in a, I'm not, you know, there's no sexual thing at all. Well, I mean, maybe, then it would really be in the money if it was. So he can detect that. So it's detecting heat from a distance, which of course there's immediate applications. I mean, particularly in the military domain. If you imagine a soldier who is about to go into a room and he doesn't know whether there's anybody in the room, he can just point his finger around the corner and just scan the room. Yeah, there's somebody over there, there's somebody over there. So he'll know pretty accurately where people are. He'll know how hot they were, for that matter, but that's neither here nor there. The other thing Ian is doing now, and he's coming into my office every day, oh, guess what we've got going now? He's feeding music into his fingers, so he can feel music through the vibrations, and we're looking at all the different frequencies, and now studying music. I mean, you know, some people who have sensory input problems of one thing or another say, oh, wait, they can feel music. Well, we'll actually be able to look at that scientifically through this particular type of input, and even analyze music and maybe try and change the music a little bit so that the person gets a better feeling or whatever. So it's an interesting way of looking at music. Of course, if we publish any academic papers on the music thing, we will have to study Beethoven and Mozart. If we study Rolling Stones and pop music and things like that, then nobody's going to publish the papers because of the academic snobbery you have to do Beethoven and Mozart. Right. This is an undergraduate student, Ashley, he got the best project prize. So literally this is doing a bachelor's degree. This was his project. This was picking up on some work by a guy called Paul Bacchi-Rita a few years ago. And initially it was different signalling input for people who are blind was the idea. And it's sending patterns of pulses in via the tongue, small electrical pulses. The person puts this on their tongue and then sends all sorts of patterns. The tongue is amazingly sensitive to different patterns. I mean, we use it. I mean, in England we don't really use it much for taste, but most other countries use it for taste and things like that, and texture. But it is incredibly rapid, the response. When you signal in this way via the tongue, why that is, we don't know. Whether there's something through evolution, we used to use the tongue in different ways, no idea, but it's incredibly quick and incredibly accurate in a strange way. He can send different patterns there, so maybe put a triangle and ask, we've got a whole load of volunteers, and ask the volunteer, right, what is the shape? And they will say a triangle very quickly, but then ask the person, right, draw the shape, and they will draw it in different directions. So some of them will have the apex at the top, so it's the same triangle. Some of them will have it up on the side, some of them will have it upside down, and so on. Yet it's been put in exactly the same way, and no matter how much we train or retrain or say, no, it's up this way, they still persist in doing it the same way. So the wiring seems to be pretty hardwired. The signals go in a particular way, and that's how again, why? We've no idea. There's hardly any studying in this particular area. So it's quite a fun project, not only helping people in some way to communicate in a different way and communicating via the tongue, but it's opening up a bit more questions, I guess, which is nice, on what's going on between the tongue and the brain. Where's the routing? How can we start communicating in this strange way? Now, talking of strange ways, we're going to shift into robots. This is still neural, and it's still interfaces and so on, but it's a little bit different. And some of you, when you think of a robot, probably think of either a human controlling the wheelbarrow robot, the bomb disposal. Or some of you may think of Arnold Schwarzenegger, or some of you may think a computer on the production lines that there used to be a lot more of in Coventry. There's still some of them, with robots now replacing humans, so that sort of thing. We need to think again about the possibilities of robots. Now, just to get us in the mood, I've got a little clip from a BBC programme called Inventions That Changed the World to show two lots of our robots. The first robot is a robot called Morgui, which, as we all know, is Mandarin Chinese for magic ghost. Now, Morgui has 5 senses, and we're integrating, fusing the input from those senses to study how, in artificial intelligence, that can work, like the human brain. But it's more the little wheeled robots that we're interested in this clip.
One of the AI community's leading lights is Professor Kevin Warwick.
Well, this is a robot head.
Dissatisfied with vacuum cleaners and robot dogs, Kevin's gone one stage further. His cyborg comes complete with
radar in its nose and an infrared top lip.
Is it intelligent?
Well, in a very limited way, I guess it is. It's sort of a basic instinct. What do I do with this information that I'm getting? How do I move? How do I operate if this signal is different?
So what's it doing now?
Well, if you clap your hands...
Oi, over here. Oh, it did it.
It's making basic decisions. All we've got it doing here is programmed to make basic decisions based on that sensory information that's coming in.
Getting the information in is nothing. That's like picking up a book. That's not an intelligent thing to do. Reading the book and knowing what the words mean, that's surely the intelligence.
Many machines can read books nowadays, but it means something different electronically to the machine as it would mean to the human.
Though the cyborg head does a reasonable job of sensing, it can't really interact with or explore its surroundings. It's fastened to its robot arm. And according to Kevin, it's only as intelligent as a dishwasher. If that's a dishwasher,
yes.
Where are these in terms of, are they dolphins, chimps?
I think you'd have to say it's about the 50 to 100 brain cell area. So realistically, you're talking slugs and snails.
But a slug and a snail, they know to eat. They know. These things don't.
They have some innate abilities.
There's no self-preservation with that.
Well, we do have the power supply. They don't have their own batteries. They each have power they're picking up from the floor here. That's where they're getting their energy. That's where they're getting their food.
But if you turned off this section of the floor,
if we turn off
and
this
what was
section,
here,
they have a basic instinct to go and look for some power somewhere else.
They
will keep going to do that until they find some.
So if I put him down,
it should go off.
So he'll have to go and look for power. Are they going to tell him to do that?
No, it's an innate response for that robot. It's a basic thing on its life. Yeah.
No, so his lights have come back on.
Lights have come on.
So he's found power.
I'm happy now that he's getting power. Away to go.
But these then are as intelligent as slugs.
It's different, but in terms of numbers of brain cells and that sort of thing, yeah, we have slugs. Probably you could say we're up to bees and wasps, the sort of tens of thousands of brain cells, is about as good as you can get.
Yeah. Bees and wasps. Right.
Now, I have to say, I know most of you don't use Wikipedia, but if you did, the original quote on there is that our robots have 50 to 100 brain cells, which makes them about as intelligent as a slug or a snail or a Manchester United supporter. But so the BBC didn't like that bit. Those particular robots there have microprocessors. That we can see how they learn, we can see how they communicate with each other and so on. But what we've done is replace the microprocessors with a biological brain in those little robots. So this is where the neural bit comes in. So the physical robot body is the sort of things we were looking at there. The wheels, the ultrasonic, so the technological body is just as you've been looking at. The brain, though, is not a microprocessor, it's not a human controlling it, not a computer in the technological sense. MEA is multi-electrode array. This is a little dish with electrodes on the bottom of it. And what we do is take brain cells, neurons, from a rat embryo, separate them using enzymes. So these are rat biological neurons, and we lay them out pretty randomly in this dish on the multi-electrode array. And it has to live in an incubator. We feed it every couple of days with a pink liquid with minerals and nutrients. It needs energy to live and to grow and connect and develop. And within about 1 week, just over a week, we have lots and lots of connections. We have a two-dimensional brain. When in fact, with neurons, you find this, Dave, you take one of your neurons out and do just experiment if you want. Just take one of your brain cells out, chop off all the different connections, and within a matter of seconds, certainly about 20 minutes, you'll see it pushing different tentacles out. Neurons have a propensity, they want to communicate, they want to interact, they want to link up, part of the genetic makeup. We can see all this happening under the microscope. So after about 10 days, we look, this is the multi-electrode array here. These rings, they're called Potter rings. This is after the guy in Georgia developed them. This is where the brain grows, develops in there. These rings are to stop it dehydrating as best we have. We have to keep it moist. It's in an incubator. It has a tendency to dry out if we don't watch it. So this helps to stop that. You can see the size of the electrodes themselves, 30 micrometers across, which is quite large. Neurons, again, take a few of your neurons out. You'll see some of them are maybe about 2 micrometers. The bigger ones are perhaps up to about 20 micrometers. This is the size of brain cells. If you do find one that's 30 micrometers, you don't win a prize. Some of them do, the odd ones do get, Nigel's probably got a lot more of those that size, but some of them get a bit bigger, but generally they're 2 to 20 micrometers. So the technology at the moment is quite large for what we're trying to do. It could improve. Typically we'll have about 100,000 brain cells. So not the 100 billion of the human brain, but 100,000, you know, it's reasonable to start with. Now, after about 10 days, we connected up to a robot body. And so what you're going to see here, this little robot does not have a computer for a brain. And there is some technology used for routing the signals, but apart from that, it is purely controlled by a biological brain. This is what it is supposed to do. Detect the wall and turn right. That's what we want it to do. What we don't particularly want it to do is change its mind, turn round, and then crash into the wall. But this is a baby robot. This robot, its brain is just 10 days old. So it's just setting out in life, if you like. The brain will be in the robot body for about 1 hour every day. And we can look under the microscope and see the brain developing as time goes by. And what we can witness is what's called Hebbian learning. We can actually see this happening. This is habitual, the type of learning by habit. If you do something, and you do something, and you do something, it doesn't have to be good or bad, you just do it and do it and do it. Because you're doing it repetitively, what happens in the brain, the connections between your brain cells become stronger and stronger and stronger. Every time you do it, the connection strengthens. This is a basic concept of Hebbian learning. We can see it happening under the microscope to our little brain. And what happens, so when you've seen, some of the time it gets it all right, some of the time it doesn't. This is after 10 days, 2 weeks, that sort of thing. And it's interesting, you'll see it, sometimes it goes, boom, there we go, just didn't work at all. Sometimes it turns round, sometimes it changes its mind. They always got a mind of its own. Well, it has got a mind of its own. This is the point. What we're trying to do is to look, put the robot in positions and look and try and figure out how memories are actually physically formed in the brain, which is something that scientists just speculate on. Some people say, oh, it's just dispersed around the brain, others it's in certain areas. We're trying to figure out exactly how memories are recalled, how they're accessed, where perhaps are they located. Certainly from an experimental point of view, can we apply new neurons, fresh neurons, can we apply stem cells to keep the memories there, to enhance them and so on. Now I say this from personal experience. My mother died just over 18 months ago, just up by the, what's the new football stadium called here? The Rico Stadium. Yeah, she was in a home up there for the last years of her life. She had dementia, and for me it was horrific to see what she was. A wonderful woman, obviously, my mother in younger life, and then the state that she went into. I'm sure a lot of you are affected by that. So for me, that was a driving force. If we, never mind the scientists saying you can't do this, you can't do that, trying to figure out some of the basics, because if we can find some sort of experimentation that might help, even if we don't really know what we're doing, then surely it's worthwhile. So it's trying to sort out memories and can we improve them long term in a basic way. Let's have a look at this same robot. This is just time step to 2 months. This is the same robot, the same brain, and it's now, all it's been doing is this particular thing in the corral. So you'll see how it performs now. So off it goes now. So it's, again, it's just the biological brain, but it's the biological brain that's developed. All we want for this experiment is for it to turn right. That's all it's trying. In other experiments, we've got it having a choice that it can turn left or right, and we could give it other things to do, and so on. And this is on 100,000 neurons. And in a way, this gets a little bit boring because it's just going to detect the wall, turn right. And I think this particular one was a model student, if you like. I mean, it just gets it right all the time. It almost doesn't change what it's doing and so on. But remember, this robot has had a university education. But I'd be obliged if you wouldn't tell the Vice-Chancellor at Reading that, because with fees now they're charging, they might decide that robots will have to start paying fees as well. But as you see, it performs well. The two things to say on this, partly because we're trying to look at things like dementia, memory loss and so on, we have human neurons as well now. I say human neurons, we actually buy them in from an American company, but it's as close as we can get to humans. That's me dead or the other thing to say, we're working with a Canadian team who they culture not in a 2-dimensional array, but in a 3-dimensional lattice structure. Now, that makes it more difficult to find out what's going on inside the brain. So the pharmacy guys on the team don't like the 3 dimensions, but from a systems point of view, it's cool, because now instead of 100,000 neurons, we're looking at 30 million neurons. So what we have is 30 million human neurons in a robot body. So it's still not the 100 billion, it's not, but it does start to get in that direction, and hence we start to get all sorts of questions, because it's a technological development. If we didn't have 30 million, if we had 100 billion, then it's the same number of brain cells as you or I, maybe more than us oldens and so on. So should it have rights? And should we have rights? And I mean, does it? What makes the difference between the human and the non-human and things like that? So all sorts of questions. Some of them at the moment more philosophical, which is nice, but some of them will become reality, because if it could have that many, it maybe could have more human neurons and so on. So there we go. We will leave our robot not making any errors and move on. To look at some other, now we're really in the realms of therapy here. Again, some of you may be familiar with deep brain stimulation. To give you an example, it is used, I know down here at University Hospital Coventry, what used to be Walsgrave, Amjad Shad, who was one of the surgeons worked with me, he also works in this area. Not sure whether you can get this treatment to that particular hospital, but you certainly can at the John Radcliffe in Oxford, where we work with Tipu Aziz. This is for the treatment of such as Parkinson's disease. And what you're going to see in this clip is a person who has Parkinson's disease. So it's a genuine patient. And he has received 2 electrodes in the subthalamic nucleus, which is right in the center of his brain. So this is for deep brain stimulation. So what you'll see is the person with Parkinson's disease, very debilitating disease. He can't walk, as you'll see, and so on. The assistants will then switch on the power packs. Now, this is an interesting thing. Any of you who are into evolution in humans must have thought, why as humans do we have all this space here in our bodies? There's not really much here at all. There's lots of organs everywhere, but here it's just sort of cavities. Well, what this is for putting pieces of technology. It's a marvellous foresight of evolution, and this is where the power packs for the stimulators, they're positioned here with wires running underneath the skin into the electrodes. So you'll see the assistant switch on the power packs, and you'll see how the patient is with purely electronic stimulation of the brain. This is a genuine patient, and this is a typical, nowadays, very much typical response.
I'd like to show you in 2 minutes what was the status of Mr. Plessman when he was referred to us by his neurologist in Belgium. And you see him before surgery without drug, unable to stand up by himself. He's helped by Patricia Limousin, who's a neurologist in our group, and he's not able to do anything of, as he will tell you, makes your life looking like normal. He's not able to walk. He has having dystonia, which are muscular contraction, deforming the different joints, and this is the best he could do without the drugs, with the help of people around him and maybe his wife and friends. He was referred because the drugs were not working anymore. He was not having any more improvement, and as he will tell you, he was just stuck to a wheelchair. This is after surgery. You see the tremor. We turn one of the 2 stimulators which were implanted with electrode into his subthalamic nucleus, which is a tiny part of the brain, and you see that in a few seconds the stimulation induces a stop of the tremor. This is still visible on the other side. We will turn on the stimulator on the right side, and you will see something even more spectacular than that. You will see that the patient feels again free, and he reset himself in his chair in the position where he feels the most comfortable. He will obey Dr. Pollack in doing some tests, even if he feels that those tests are a little bit useless as compared to the feeling he has. He can do that almost normally. On the right side, should I go longer, as you say? And we'll show it on the other side. And then he will walk, he stood up alone. He's without any drug. You see him walking, turning. It was a few days before the Vienna meeting on movement disorder.
Now, that particular device works very well, but it does use a lot of power. And certainly Tipu, the surgeon we work with, there is a potential external rechargeable device, but it means the person has to lie on a bed for hours on end, which almost defeats the object of doing it. So Tipu doesn't use the recharging device at all. Patients just don't want it. But that means that this battery runs down after 18 months to 2 years, and the patient has to go back into hospital simply to have the batteries replaced, which involves surgery, which they can get infection from. It's expensive because it's neurosurgeons doing it, so it's a bit of a problem. So what we're doing, working with Tipu and his team, to make the stimulator intelligent, so it only stimulates when it needs to stimulate. The problem is it needs to know when it needs to stimulate, and needs to stimulate before tremors actually start. If it doesn't start until the tremors start, then the stimulation doesn't have an effect for about 10, 15 seconds. So what our artificial intelligent device has to do is to monitor the electrical activity in the brain and then predict when tremors are going to start before they start. So literally what it's doing with a very simple, I mean, it's a multi-layer perceptron, is perfectly okay, relatively simple artificial neural network can model very well this particular region of the brain and predict 15 to 20 seconds ahead when tremors are going to start. So effectively, an artificial neural net is modeling how part of the human brain functions, better than the person themselves. The person themselves doesn't know they're going to have tremors start until they actually start. The artificial intelligence system does. It waves a flag and said, this is going to happen. And we're using that now to provide a feedback loop with the surgeon so that the stimulator kicks in when the artificial intelligence system tells it to, rather than operating all the time. So it's a medical use of AI. The last area I'm going to cover before we have an experiment is looking more at enhancement. Now, we've been looking at increasing your range of senses. Okay, that's one area. We have typically 5 senses, all sorts of signals going on in this room, ultrasonic signals we've seen, we haven't seen, we've talked about ultraviolet signals, X-ray, so it goes on, which as humans, we just don't take those signals in. It's not that they're not important, of course they are. I mean, our input spectrum in terms of senses is very, very limited. And our whole perception is based on a limited set of signals from the outside world. We're trying to make our understanding of what's going on from a limited piece of information. So why not extend? I think of all the things in terms of enhancement, communication for me is the big one. Because if we compare how humans communicate with even a standard PC, I mean, we have to be embarrassed, surely. We're so far behind technically, it's unbelievable. I mean, if you imagine what's going on, a human brain, highly complex electrochemical signals, all sorts of thoughts, images, feelings, emotions, ideas, that's what's going on in our brains. Then we come to communicate those. What do? Well, we convert them into trivial, coded, mechanical pressure waves that bear almost no relation to the original thoughts that we have. I mean, in the university system, there's a constant problem we have. We tell the students, comes to exams, have they got any idea what we're talking about? No, because they're probably thinking about something else, weren't even listening to what we're saying about. But it's such a limited, even if you've been married for 30 or 40 years, you still have no idea what your husband or wife is trying to actually, what do you mean when you say that? Why don't we just send signals from brain to brain? Just never mind, for the students, it doesn't matter if they're thinking about some film or a girlfriend or a boyfriend. Zonk, there's the message. I mean, we probably don't need to have exams after all. We know they've got the message. So it's really looking at the possibilities of communicating like technology does, in parallel, lots and lots of signals, communicating in terms of feelings, emotions, thoughts, really extending the way that we communicate. That, to me, is a really good reason for looking at research in this area and seeing about the possibilities of enhancing, even if it's just the way we communicate. But then there's others, link your brain to a computer, start to think in more than 3 dimensions, why not? Now, let's have a look at what I've actually done in terms of experiments here. First of all, though, to give us an idea of this therapy enhancement divide, this is Campbell Aird. We'll see this hand again in a moment, but one of the problems, Campbell lost his arm due to cancer. He's been given this robot arm, but you'll see him flicking the switch to control the robot arm, which sort of defeats the idea in a way, having to use this hand to control that hand. What would be much nicer if he could control this arm and the hand directly from his brain and actually feel what the hand is feeling in his brain. Surely that would be what we want. But what this would mean is an interface between his nervous system and the wires, bi-directional, sensory signals up and motor signals out. Fine, let's assume for a moment that we have a wonderful interface that provides that. What we are then getting are brain signals, not just on the nervous system, but brain signals down here on the wires. Great, we can therapy. Give somebody an artificial arm or an artificial leg if it's mechanically okay and so on. Fine, that's the therapeutic. But now we're talking about brain signals on wires. Hey, great, we've got signals on wires. What do? Let's plug onto them, let's send them somewhere else. So what we're looking at here is once we've got that bi-directional interface, your brain and your body don't have to be in the same place. Because you can plug your brain, your nervous system into a network, and your brain can directly control bits of your body wherever the network takes them. If you see what I mean, the network becomes your nervous system. As long as we've got it, all it takes is a bi-directional interface, simple little thing, and then your brain can control pieces of technology on another continent, as though it's your body. It is your body, as far as your brain is concerned, or even on another planet, and can pick up sensory information from wherever it comes and understand it, perceive it, infrared on Mars if you want. The technology is there, as long as we have just this simple little bi-directional interface between the nervous system and wires technology. So what have I done? Well, here's me on the operating theatre. This is Amjad Shad, who now works at University College Hospital. Some of you may have come across him or know him from there. This was at Radcliffe in Oxford. There were 4 neurosurgeons involved with the experiment. This was a research project from the surgeon's point of view. What I actually had implanted was this little device here. This is referred to as the Utah array, also called the brain gate system. It's 100 electrodes, 100 spikes. The electrodes themselves are typically about 2 micrometers, so they're the right sort of diameter for nerve fibers and neurons and so on. This was fired into the median nerves of my left arm. It was a 2-hour neurosurgical operation. Just to say, this was not for medical purposes. I didn't have a problem that I was having this for. Well, I had a problem that I'm a scientist, and it was a research problem to find out partly how could this work for somebody who's paralysed, to connect up neural signals to technology, but also just to look at some different examples of enhancement, as you'll see. So this was in my nervous system for just over 3 months. Sorry for those of you that have eaten or anything before you came here. This was from the operation. So this is my left arm during the operation. They had to make 2 incisions, and then they pushed this tube down between the incisions, and then pushed that array of electrodes down the tube, because you can't just push arrays of electrodes down the arm, otherwise you've got bits of bone and tissue and things like that, you get stuck. They then removed the tube, hammered the electrodes into my nervous system, a little pneumatic hammer, and then for just over 3 months I had the electrodes in my nervous system, wires running up my arm, and the wires came out onto this connector pad here. So these gold terminals were directly linked into my nervous system. So when I opened and closed my hand, we could pick up here the neural signals very clearly. They're very different to other types of signals that were doing that, causing the hand to open and close, send those signals into a computer, either by hardwire or by radio, to get different things to happen, but also send signals down into my nervous system that over a 6-week period my brain learnt to recognise. So I had to learn to recognise the pulses, and then we could use those nerve fibres for different experiments, as you'll see. So I've got a little clip from Discovery to show some of the things I could do.
One man in tune with technology is the world's first cyborg. Part man, part machine. Kevin Warwick, cybernetics professor at Reading University, England, took a leap into the future as long ago as 2002. For 3 months, a silicon chip was implanted into the nerves in his arm.
At that time, no human had had an implant of this type before.
It was a procedure that until then had only been tested on chickens.
Would the body reject it? Would it affect the way I moved or my sensory capabilities, and I could have lost the use of my hand? Could it affect my brain? Ultimately, could it send me crazy?
Kevin was plugged into a computer which monitored the nerve signals from his brain to his arm, receiving and transmitting them as radio waves. With the signals from his brain, Kevin could not only turn on lights, he could control a wheelchair. And from 5,000 kilometres away via the internet, he succeeded in getting a robot hand to mimic his own hand movements. His most impressive experiment involved his wife, Irena, also having a chip implanted in her arm.
The communication experiment between myself and Irena was vitally important to me. This was the highlight of the whole experiment.
Kevin wanted to discover if it was possible for his brain to receive and feel signals from Irena's brain.
When Irena first moved her hand, it actually felt like a charge running up my index finger. It was a phenomenal feeling. Literally, every time she moved, my brain received a signal. There we were communicating for the first time in the world, nervous system to nervous system.
It was the first time two people had electronically communicated by thought alone.
In the short term, we're going to see implants used to help people who are paralysed switch on lights, operate the TV, just by thinking about it.
In 30 years, he believes we'll all have chips in our brains.
But ultimately, having extra memory, having downloads from the computer, uploading from the brain. Earth is going to be controlled by cyborgs. Humans are going to be something of a subspecies.
He will be half man, half machine, with super memory, super senses and superpowers.
I think quite clearly that's where we're going. Superhuman. So a little bit of Nietzschean philosophy for some of you there. A few holiday snaps just to finish off with. Ultrasonic sensors again. We've heard this sort of thing. It's the same to the sensory input. This time for this experiment, the output from the sensors was fed into my nervous system. So what was happening, if an object came close, my brain was receiving pulses of current that increased in frequency the closer the object came. Further the object away, the pulses died away. So with a blindfold on, I was able to move around and detect where objects were. I didn't know what they were, but I could sense where they were. And if there was a slight movement, really high degree of accuracy at detecting the movement. Dependent on the sensors, of course. But if you want further sense or shorter, depends very much on the sensors you use. This is my wife, Irena, helped in a number of ways. This was some jewellery that a student at the Royal College of Art in London put together. And the jewellery changes colour from red to blue and so on. And it was linked to my nervous system. Now, obviously, I could operate it by opening and closing my hand. So literally, my nervous system controlled my wife's jewellery. So if any of you guys here thinking what to buy for the wife for Christmas, this is the thing. Hey, it's from my nervous system. Now, perhaps, if you can imagine this, the way of operating, different on the nervous system, there are all sorts of different signals that you can pick up. Ros Pickard is picking up signals to do with anger and stress. Drivers in Boston, so monitoring the nervous system. If I was to go, shock is another thing. If I was monitoring your nervous system there, I could have picked up shock. If you're just the audience participation. Sorry if anybody woke up or anything like that. Excitement is another one. Clearly you can measure it on the nervous system. So picture the scene. I am calm and relaxed. My wife's jewellery is blue. I get excited. My wife's jewellery starts flashing red. She worked at a completely different place. She didn't work in Reading University. There she is in her office. Jewellery is blue. Fine. He's not doing anything he shouldn't. And the jewellery starts flashing red. What is he doing? And who is he doing it with? Maybe it's not such a good idea. This was taken at Columbia University. Some of you may have noticed Ghostbusters was on the TV the other day. Columbia University. They also do research there, and what we did was plug my nervous system into the internet, in real time. So it actually had an IP address, my nervous system. The only security really we had, we did have a security company on board, but really the only security was we didn't tell people we were doing it until afterwards. So if you had struck it, you would have been able to send signals into my nervous system. But we linked up from my nervous system in New York to the robot hand, the same one we saw before, this time in Reading in the UK. I moved my hand in New York, my neural signals across the internet to move the robot hand. When the robot hand gripped an object, signals were sent back from the fingertips across the internet to stimulate my nervous system. So my brain received increased pulses in terms of frequency, the more the fingers gripped an object. So it was a straightforward thing. I was trying to open and close my hand in New York that opened and closed the robot hand to get it just to grip an object. That worked very, very well. So again, it can be used for somebody who's had their hand amputated to control an artificial hand, but you can extend your nervous system if you want. And then the final bit, I have to say I have a communications background which stems from my early years. After I'd left the sheriff, I went to do my apprenticeship, which was now BT, it was then the GPO, and worked for a fair bit of time in Little Park Street Telephone Exchange. I don't know whether it's still. And just as an aside, if any of you in the year 1972 found that you couldn't get through to directory inquiries for a couple of hours, it was me to blame, because I was supposed to be cleaning the switches and I busied them all out until one of the supervisors came down and said, "What the hell are you doing?" So it was my fault entirely. But there we go. But those days in communications led us to do this experiment. What my wife had was small electrodes pushed into her nervous system by the doctor. If you try this later tonight, you will find it is extremely painful. And we thought she was going to get some anaesthetic for this, but the doctor that did it said, no, I need to make sure I've made a good contact with your nervous system. So he pushed the electrode in, she screamed, and the doctor calmly said, "Oh, I think we've made a good contact." He pushed another electrode in, we went back to the lab, and electrically, I mean, you can see that the two connections into the electrodes and so on. We went back to the lab and electrically connected our nervous systems together. So when she moved her hand, my brain received a pulse. So it was like a telegraphic communication, a very simple one, tick, 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 in terms of the brain. So very simple telegraphic communication, nervous system to nervous system. Clearly, where that is going now is not just nervous system to nervous system, but brain to brain. And that's where my research is heading just at the moment. It's looking to carry out the first brain-to-brain communication experiment. Will be similar thing, telegraphic to start with, but then as communications we know have moved on, hopefully this will move on as well. Irena is not so keen. For some reason she thinks that it's a bit dangerous, the brain implant. So if there is anybody who wishes to volunteer, please let me know. That's all for the presentation, but what I'm going to do now is to, if it's all right with Pat, we'd like to do a bit of a demonstration experiment, if that's okay. I will need some volunteers, like about 6 people, something like that, but what I would prefer is a mixture. I don't want this to be just a guys thing, rushing forward and here's the guy thing. So if it's possible to get 3 guys, 3 girls, we're not going to do any sort of naughties, there's no sort of swapping going on. This is purely an experimental thing, just want to get a bit of a mixture, and probably the person that tests the extrasensory input will need to be a little bit shorter than the others. So if you're a taller person, come, you can help, but you'll probably be one of the trees that I'm going to use. But if I could ask somebody, I need a hand to get this table out of the way, first of all. So please, I need about 6 people, would be great. And a mixture. Excellent, that's great. Go on. The longer you take, we've got to stay here for ages. That's perfect. This is absolutely brilliant. And who fancies? Do you fancy you go with the? You do. Okay. So I'll explain first of all to everybody what's going on here. This is an ultrasonic hat. So as you've seen, the ultrasonic signals. Now, we're just going to have to make a small incision into your... I hope that's okay. Did you bring a tissue or anything like that?
You asked the wrong person. I inject myself 4 times a day.
Hey! What we've done instead, to be honest, is convert, just for demonstration purposes, to convert the ultrasonic signals down, so I'm going to hope this works. I mean, they never do when you have a demonstration, do they? Down into the ultrasonic sensor, the ultrasonic sensors down into these little buzzy vibrations here. And I notice I've got to reconnect this one up to start with, which is not so easy to do when I haven't got my glasses on. Let's come up in the drive out. Let's just check that this is working, which is not working at all. So let's try it out first of all, and let's see what you get. So that should be your right hand one, and that should be your left hand one. There we go. So let's see what we've got working to start with. So we've got half of it working. You might have to go with it. So, what's happening, just to demonstrate, is that when something comes closer on the left-hand side, the little buzzy vibrator goes on the left. When something comes closer on the right-hand side, the little buzzy vibrator goes on the right. So we're converting the ultrasonic signals into a sort of a sound, but a vibration. And what I'm going to ask you to do, I'm going to make it a little bit more difficult. Let's turn it off for a second. Is it, take your glasses off? Or?
Yeah, that's fine.
There we go, sorry.
No, I definitely can't see.
Well, just to be sure, but it's all for the visual effect. There we go. So, how many fingers am I holding up? Good guess, good guess. There we go. And all I'm going to do in a second, when I switch it on, I'll take you to this side, is to ask you to walk across to me, and I'll be shouting to you, but you've got to try and avoid hitting anything, okay?
Yeah.
Now, you guys are objects or trees, okay? So what I want you to do is to try and, I'm going to be over here, so if you can sort of scatter yourself in a tree-like fashion. Sorry, what's your name, by the way? Okay, thanks very much. Between Anne and myself. Now remember, you are trees, so trees stay where they are, but trees, you can do tree things, you can sway, but you don't jump around. Trees don't mostly tend to jump around unless they've had neural implants and things like that. Right. Now I will be going off the air in a second. Let's just check.
They're both
There. Good, we're working. I'll go off here for the moment. So I'm just going to shout for you to come. Can you hear me okay?
Yeah.
Okay, so if you come towards me now, and remember, try not to hit anything. This is really trying to give people an idea of how quickly you can take on board an ultrasonic sense and make use of it. Yeah, you can punch trees, or if you like, you can.
I've got it now. Yeah. If I move my head, then that's.
Yeah, you've got it. You can use it. It's a different sense. Yeah, yes, yeah. Perfect.
There's nothing if I go straight on.
This is perfect.
And then that's.
You can pretend to be a dog if you like as well. These trees are on for it.
If I were a male dog, then it might be...
Exactly.
Yeah.
Well, so it's your game at the moment. But you're doing exceptionally well. You're doing really well. But you've got it with the scanning.
Yeah,
That's perfect. Taking the scenic route now from an ultrasonic sense. You're doing very, very well. Remember, heading to me. You can kiss the trees if you like. That is an option. You're doing very, very well. Yeah, still over here is where you're coming.
Yeah, it's just avoiding the buzzers.
It's quite unnerving, isn't it? Because you're not sure if there's anything there or not. You hear me? Yeah, getting very, very closer. You've done very, very well. Big hand for It's one once you get into it, isn't it?
It was easy to trust it. Once I realised that moving my head, I could scan and and I was feeling for lack of buzz on either side. Yes, I think it would have been the other way around.
Well, there was another experiment. Thank you very much. It actually worked. Thank you very much. Can you give them all a hand? Unfortunately, I know the pantomimes I went to at the Hippodrome, so they would have little free, I think Tommy Trinder was, if anyone remember him, was one of the first one. Used to have little goodie bags for the kids that got up on stage. And Coventry University, are they going to provide? No. Okay, well I hope that's given you a bit of an idea in a different way how the human brain can adapt and take on different sensory input and make some sense and use of it fairly readily. We just used the ultrasonic example there. Infrared is not too difficult as well, and so on. Hopefully you can see the potentials for extension. Thank you very much for coming tonight. Happy Christmas again, and yeah, I can take questions. Yeah.
On the very first thing that you did with the neurons in the brain, how did you know what to connect to where on the 100-odd connectors?
This is the rat brain robot, as I call it. What we did after the 10 days, when it's really developed innately, the neurons have grown, they put out a lot of tentacles, each of the neurons, and you get the sort of small world thing happening. So neurons that are close together tend to make a lot of connections, but you still get these long connections which seemingly can be quite thin and not important, but they have an effect on what's going on. We pull round the electrodes, so if I pull back to that particular slide, we will try different electrodes and see where we get a response on other of the electrodes within a matter of a few milliseconds. So, yeah, if I pick up that one, so maybe if we numbered these electrodes and said, this is number 21, and we find when we stimulate number 21, within a few milliseconds we get a response on number 68, let's say, 20% of the time. This is through quite a complex neural pathway. When we're getting a reasonably repetitive response, then we connect that up. So it's an innate development which we then use to start off with the robot. So that's what you saw straight away. Sort of 20% of the time the robot was getting it right, as it were, what we wanted it to do, and the other 80% it was getting it wrong. But the interesting thing is then, because it does it and does it and does it, this habit kicks in, this Hebbian learning, and that pathway strengthens and strengthens and strengthens until you get the sort of performance that we saw at the end.
So you find out the ultrasonic, and the ultrasonic came back.
Oh yeah, sorry. Yes,
and then it said to turn right.
The ultrasonic will stimulate this thing, bing, 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 and this out is so this is like a sensory input signal, and then you've got a motor output which changes the direction of the robot. And of course then you can immediately make this more complicated. You can have an electrode there which causes the robot to turn right, another one causes it, different one causes it to turn left, another one causes it to spin. You know, you can make it as complex as you like. You can make the sensory input as complex as you like, which is what we're doing now. I have a master's student who's putting audio input so that we can click and whistle and get it to do different things with different sounds. Potentially, we can give it an audio output as well. And of course, you know, we can get it to speak or what it will say, help me, or something, I don't know what, for those fans of The Fly and things like that. I don't know what I mean, we could get it to do all sorts of things. As we increase the number of neurons, it does need more input. I think that the ultrasonic input really is not, it's sensory deprivation for the robot. It's really not a lot of sensory signals going in, and so increasing the sensory range really is important to give it something to do, to give it a sort of, you know, it gets a bit bored, I think, otherwise. described it, we don't use a reward scheme. It is purely habitual learning, simply because it does something, it does something, it does something. So there's no reward. We have the feedback loop, and we use that to start with to, it's a feedback loop that we see how it's developed in the brain, and then use that as the feedback pathway. Now we can reward or punish it chemically. We can look at if it's doing something that we want it to do, turning right at a certain time. We can apply but we have to figure out in the brain what sort of pathways are likely suspects for that particular good behaviour. We can then apply chemicals to that region of the brain or around that pathway that enhance the growth in that region. So there are more connections, the neurons link up more and more, it becomes more likely that that particular action is carried out. And we can do the opposite, we can punish chemically. We can literally go, and if it's doing something we don't like, we can apply chemicals to that region of the brain. It's like giving it a lobotomy, effectively. We can either restrict growth or even kill off neurons in a particular area to stop it doing something we don't want. Electrically, don't know at the moment. That's not me saying we don't need research. We don't really know. With actual rats or animals, even monkeys, of course it's pretty well, and even humans I guess, it's pretty well known where the pleasure zones are and where pain zones and so on. And so somebody like John Chapin, if you Googled him, what he's doing is putting electrodes into what he describes the pleasure zones and the pain zones, and he gets rats going round a maze by pressing a button on the computer that says turn right, turn left. So he describes it as stimulus cues. But I mean, what's actually happening, either the rat is getting, hey, yeah, that's great, I'll go left, or, it's getting pain. But that's, we don't know at the moment, really, in our developed, the cultured brain, are there such zones or where they're developed and so on. I mean, if we could figure that out, then potentially we could start applying electrical pulses and other things that could reward and punish it. If we get more inputs that start to be meaningful, again, then you can start to, but you're then implying that the brain could start to think deep thoughts and start making value judgments as whether it does this or does that. So it starts to become a lot more complex very quickly. But at the moment, reward and punishment is purely a chemical thing that we can do with a fairly long payback.
We probably ought to leave it at that point and perhaps nobble Kevin downstairs afterwards, otherwise I think your food will have disappeared. So are you going to say a few words, Derek?
Well, I mean, what can one say? I don't have a brain large enough, I think, to say how much we applaud the work you're doing. I do suffer from Save the Children's Fund. Oh no, sorry, it's the one next door. It's age concern.